1. This is some examples of for chapter 3 of projectile motion. So some examples. All right, now we're going to be looking at the example of objects thrown horizontally or tossed horizontally, and it lands a distance x away and falls a distance y. Right. This compares to our problem of when we launch a projectile. Again, it follows a parabolic path, and if you launch it at some angle theta with some velocity, this distance x is the range, and as we've seen, if you launch it from the same height, which is all we're doing, the range is v naught squared sine twice of the angle over g. Okay? So that's what we have here for this. All right. But, you know, we've talked about that. Here's some examples. I'm going to do some examples, just this part here of just launching it horizontally, because here we have a simple case here. All right, we can, you know, there's certain things we can look at here. All right. And the example I like to look at is, if you ever watched videos of, you know, from World War II or anything where they're dropping a bomb from a plane, you'll notice when they drop it, the bomb falls straight down from the plane because they're both going at the same speed. All right, so the thing was, well, if you're going to drop it on a place, you know, and if you're, let's say, 1,000 meters up, all right, 3,000 feet, which is probably a low end, all right, I mean, they'd be upwards of 5,000 meters more as far as how far it go. All right, now, so let's do, you're launching from 3 miles high, 5,000 meters high, you launch a plane. I mean, you would not just drop it. If you're right over where you wanted to drop it, you dropped it, it's not going to land there. It's not going to go straight down. We already know what's going to happen. If the plane is moving, say, at a constant velocity of, let's say, you know, for World War II, let's say 100 meters per second, which is about 225 miles per hour. All right, and you drop it from 5,000 meters, there's a few questions here. Where is it actually going to land? It's not going to land straight there. It's going to go something like that, right? And so this would be y, this would be x, and the question might be is how long would it take to fall? And how far down is it going to be from where you drop it to where it actually lands? This is part of what we had in World War II. The Norden bomb site was trying to figure out how to make this work. So you're actually dropping some way in front of you. So let's look at this problem. So y is 5,000 meters. And we know from chapter 2 that, you know, our equation y for just something in free fall, because we're going just horizontally, free fall, y is 1/2 gt squared. And for the problems I use, and again, I'm just going to do approximate. I mean, if I was doing it in real life, I would have it use 9.8. So it'd be 5,000 is 1/2 times 10 times t squared. That's 5,000 divided by 5, which is 1,000, equals t squared. So t is about 31.3 seconds. Which is quite a long time, you know, half a minute for it to fall that far. All right, so that's how long it would take for it to fall. In the meantime, if it's going 100 meters per second, 225, how far downstream is it actually going to fall? All right, well, x, all right, here, in this direction, acceleration in the x direction is 0. So our expression for x is going to be, back from before, v is x over t. So v, x is going to be v times t, right? So that's going to be 100 or 3,130 meters, you know, which is about 2 miles. So the thing would actually land 2 miles down from where you actually dropped it. And that's the problem, you know, that's the problem with you drop something way up, it's gonna travel far away. It's not the concept of it going straight down because it's gonna lose its speed. You appear to see it moving straight down because you're moving along with it as it falls. So you're going along as it does that, and you're here, you're here, you're here, and you're here. So x is 3,100 meters, almost 2 miles. All right, so that's an example of that. All right, let's try something else, another bit, something on a smaller scale. So if you have any questions, let me know. Again, this is just for free fall, or where you just let it go. Why is that? All right. All right, let's try something a little different, and this is how we actually used to do. When we look at projectile launcher, we'd be doing labs before we have computer analysis and such. And the way we're looking at projectile motion is we would try to use a projectile motion in different ways. So I have a table. This table's about 1 meter high. We would have a launcher that would shoot a ball straight sideways at some speed. We don't know. And what we would do is try to figure out how fast this thing was launching it. So launch a ball and we'll go flying out. All right? So the question is, how do we find that initial speed? Nowadays we'd have a camera, you can actually film it as it comes out, take a digital analysis, and go from there. So the question is, how do you actually do this problem? And so what we figure out, this is y, this is x, so what we'd actually do is launch it, it would land a certain distance, and let's say it landed, we do measurements, and landed 2.5 meters away, all right? Because that we can measure. We launch it, we see where it lands, we can measure. That's the thing we could actually measure with no technology at all. We just observe where it lands, we measure that with a ruler stick, and then we can go from there. That's the only thing we have. Based on that though, what do we do? How do we solve this problem of the initial speed? How do we go back to there? Well, there are a couple things here. We have the ball is in free fall in this direction, and it has x is constant in the x direction. So the question, so how can we use this? Well, we have for free fall, again, we go back to our equations, we have v naught in the y direction is 0. We'll use y naught as 0. So it's just dropping. So for free fall, y is 1/2 gt squared. And again, I'm going to use g is 10 meters per second squared, just to make the problem simpler and less numbers to deal with for solving it. Okay, we have that information. We also have in the x direction, v naught, which continuous goes to the same speed, because if we plot the graph of velocity in the x direction versus time, it's going to be a constant. All right? So we have v naught is x over t. So we have a few things here. If y is 1 meter, and again we can measure that easily with a meter stick, and just to make it simple, we have it fall 1 meter out. We have it fall 1 meter, and it falls off out 2.5 meters. All right. Well, from there, we know what g, we know y. We can figure out how long it takes to do that. So 1 would be equal to 1/2 times 10 times t squared. So that would be 1/5 equals t squared. So that would be 0.2. All right, point t would be 0.45 seconds. And I can do this if I dropped an object, if I dropped an odd meter, it'll take like half a second for it to fall. All right, now we know how far we have x, we have t, we can figure out how fast it's going. So to get v would be 2.5 over 0.45. Would be v naught is 5.5 meters per second. And that would be the example . So that would be these two kind of examples of projectile motion. One, we know how high we are, and we can determine how, based on how fast we're going, we can tell how far out it goes. And this one, we know how high it fell from, and we know the speed, the distance it traveled, and from there we can